So, can I continue? Or there is still someone missing? Okay, then I will clean the table and blackboard and... There we go. Good. And now, very important connection. So this is a very important things, like this is the connection of the first and second quantization. I will just write it. It's still the same chapter. So connection with first quantization. And this is a super important formula. So the question is that assume I give you this, okay? And then assume that such that if I'm summing over R all those occupation numbers over all entries of this infinite vector, that I'm getting some n which is finite and larger or equal than 1. Okay? The question now is, and your colleague already was asking that question, like how to connect it, it's boson or fermions. And now it's up to us. So we can say that it's boson or fermions. So we need to write the wave function for that state in the first quantization. So what I am doing here, I am writing the wave function, and we know that altogether I am having n particles in the system. So my wave function should have n arguments, R1, R2, up to Rn. Okay? So I should be able to write some wave function which have n positions or positions and spins. In principle, I am not taking the position about the spin. And the question is, what is the corresponding wave function? And the answer is here. So I'm just writing what is it. So it is this n factorial, which is the sum of those guys, divided by n1 factorial, n2 factorial, etc., and omega factorial. And I am taking the 1 over square root of that. So this is the square root of this. And now I am making this symmetrization or anti-symmetrization. This is up to us, whether we want to do fermions or bosons. Okay? So I need to make the symmetrization or anti-symmetrization, which we know what does it mean. This means this summing over all possible permutations. And what we are now permuting is the following wave function. And I will write here what we need to anti-symmetrize or symmetrize. And that would be the, I am taking, okay, so n1, so alpha 1 at position R1, alpha 1 at position R2, alpha 1 at position R1, Rn1. So I need to take n times or n1 times the wave function number 1, because this slot stays for the occupation of the state alpha 1. And this tells me state alpha 1 is occupied n1 times. Okay? Now, I am looking for that slot. There is wave function alpha 2, and the wave function alpha 2 is occupied n times 2 times. So I am now continuing. So this is alpha 2, and now I am having the vector Rn1 plus 1, alpha 2 Rn1 plus 2, etc. alpha 2 Rn1 plus n2. Okay, all those guys are done. So this is done n2 times. Okay, multiplied. And I'm going and going and going and going. Let me still write it like that. So then there will be alpha free state. Okay, alpha free is occupied n3 times. So I need to continue. So and then we'll write it the alpha free r n1 plus n2 plus 1. Alpha free at point r n1 plus n2 plus n3. Okay, I need to make it n3 times. And then I am going, and I'm coming to the wave function alpha omega, which is the last guy. And I see there are n omega particles in that. So what I need to take is alpha omega at point r n1, n2, n3 plus n minus 1, or n omega 1, sorry, n omega minus 1 plus 1, okay? And I'm going times alpha omega at point r n1 plus n2 plus n3 plus, okay, you see that it stopped to be less and less funny. And the last guy will be alpha omega r n1 plus n2 plus etc. plus n omega. Okay, so you take this big object, and now you need to make the symmetrization or anti-symmetrization of those arguments. Okay, making all those permutations which we discussed. Okay, but this is the connection with that. If you really would like at some point to write the wave function, this is the way how to do it. Okay, so this is the communication between these two representations. Wave function representation and some abstract occupation number representation. And this is very important formula. So I will call this, because we will use this formula many times. We will use this formula to understand how to express operators in this Fock space. Maybe we know how the operators act here, but we would like to know how they work in the Fock space. So I will call this equation as an equation, as a very important, so I'm calling it equation heart. Okay, so several times I will say C equation heart. Okay, so it's, do you understand the meaning of that? It's pretty clear. So it's exactly what we said. So this is the occupation numbers of these given wave functions. So if we would like to create this big wave function, we need to do it like that. Okay? And we see that if this, for example, would be larger than 1, for the case of the fermions, then the anti-symmetrization will take care and there will be not any physical wave functions corresponding to it. Yeah, so this will tell us that state 2, 0, 0 for fermions is nonsense. Such wave function does not exist. Okay? So, good. Great. So, and if I would have now generic wave function, which also has a, like if I would have now the wave function psi, okay, this psi was also psi, so be careful, psi. So if you do with this linear combination, then if I would like really convert these to the wave functions, then I need to do it with each of these guys, as we did before, and then I will get some complicated wave function in the real space, which will be linear superposition of states with different number of particles and things like that. Okay? So these things, if you will really write it, then you will see that there will be things that the wave functions of that type, wave functions of that type, there will be the wave function of that type. Yeah, because I can have different things. So this will be linear superposition of many wave functions with different number of arguments. Okay? You see it? Okay? Guys, give me some signal that yes, no, I am confused, I am fine. Who is confused? No, let's better. Who is not confused? But it's nice you say, so you are confused? Okay, who is not confused? 1, 2, 3, 4, 5. Who is confused? Don't shy. 2. So what's the problem, guys? Here, you mean that? No, because I can, for example, I can take the wave function because it looks like that it will be some coefficient, I don't know, 3 times the vector 1, 0, 0, 0, 0, 0, plus, I don't know, vector e, and it will be 1, 1, 0, 0, 0, 0. Yeah, so if I now make out of this the wave function, to do with the wave function, which will be 3 times c, which depends on one wave vector, and there will be imaginary times, and there will be some other wave function, which depends on position R1 and R2. So such wave function in principle is a superposition of things, okay? Because I just want to say that, just to be prepared for that if this happens. Great. So this is the Fock space. And what we now need to do is that, as I told you, we are having quantum mechanics, we know how the operators look like in the other representation here, so we know that, for example, the T can be the kinetic energy, which is h bar squared divided by 2m Laplace operator, okay, with a minus. Or we can have, I don't know, angular momentum operator, yeah, or we can have momentum operator, or spin operator, or any operator, which we normally know how they look in the Schrödinger equation. And the question is, we need to transform this operator to the Fock space, such that we know how they're acting on the Fock vectors, okay? So this is the next task, what we are going to do. Because then we will do the physics in the Fock space. Okay? Good. So I ordered the coffee, and I hope it will come. So, okay, so we are going to the next paragraph, and this is the creation and annihilation operators. And you were also confused. So what was confusing you? You said that you're also confused. What is the meaning of? Can someone symbol?
He's asking the meaning of the pi SA.
This is the symmetrization or anti-symmetrization procedure, which I was describing before when I write these sigma permutations. I wrote some object and then I wrote the sigma, and I said it's getting out of the permutation. Do you remember? Plus minus 1 to the power of sigma and permutation group. So this P means that. Is that clear now? So let's say I can have I was writing something like that, alpha 1, alpha 2, alpha 3. And I wrote it, for example, this is the anti-symmetrization of this alpha 1, alpha 2, alpha 3. And I wrote it like that with this vector. And what does it mean? This was meaning that we were making all possible combination of these things. So it was something like 1 over 3 factorial. And then since I'm doing anti-symmetrization, I need to take care about the permutations. So this is minus 1 to the power of 1 of 0, because there I am making 0 number of swaps. And then I will write it alpha 1 at R1, alpha 2 at R2, alpha 3 at R3, right? Then I'm making the first swap, so then I get the minus, and it would be alpha 2 at point R1, alpha 1 at point R2, alpha 3 at point R3. Then I'm, let's say, making other swap, so it would be plus alpha 2 at R1, alpha, okay, I made the swap here, alpha 3 at point R2, alpha 2 at point R3, etc., etc. So I'm making such things. This is the symmetrization or anti-symmetrization. So this symbol means that, okay, by that I still mean to do this. Okay? Clearer? Okay. Good. Good. So, we go on. And we go to chapter paragraph 3.3. And this is the creation and destruction operators. Also called annihilation. Operators. So that's as I was explaining you. So if you are in the first quantization, here we have a wave functions, which are truly wave functions, some functions of some number of variables, and we are having operators, and these operators are operators which are depending on the positions, which can depend on the derivatives, right? Higher derivatives. So this is the standard thing which we know from the quantum mechanics. So this is the operator in the quantum mechanics. Now we are in the second quantization. And we define some crazy Fock space, and then we are having a generic vectors. And now our generic vectors are some strange linear superposition in principle in the state occupation basis. And the question is, if I have a such operator, what kind of operator is here? And the story is like that. Take this guy, bring it to the wave function, use the equation star, or use the equation heart, which was before on the blackboard. So we know which wave function it is. Now apply the operator. Okay, you apply the operator. So you get another wave function, phi, R1 and Rn. And then again use the equation star, equation heart, such that you will get new state phi expressed in that way. And if you are looking, maybe you can directly find the operator which goes from here to here, and we don't need to do this. But this is the logic in principle. If you are lost, then you need to do it like that. You write it, you transform it, you work, and you go back. If you are clever, you can maybe try, and then you say, oh, it's like this. Okay? And you have it. So this is the way we want to do. And we will see that we can define in this Fock space some special operators, which are these creation and annihilation operators. And we will see that each operator here, we will be able to express as an operator here in terms of the creation and annihilation operators. Okay? So the answer is surprisingly simple. However, procedure is tedious to do it. Okay? And I will not show it. I will just write the results, how it is. Okay? And you can then see some books when they are doing, and it's combinatorics. You are dying, many indices, symmetrization, anti-symmetrization. So it's just the hell. Okay? But the logic is that. It's important you understand the logic. Okay? Great. So we are going to do it. And the good thing would be that we define such operators in a special way, such that there will be automatically taken care about the statistics which we are doing, the bosons or fermions. So even we don't need to care about that, whether there is symmetrization, anti-symmetrization. Just we'll say we do with the fermions, then we are having some fermionic creation and annihilation operators. If it's boson, we are having bosonic creation and annihilation operators. So also the care about the statistics will be done for us, okay? And this is this practical economical way how to keep these informations relatively compactly written in some expression. But if you really calculate something, then things will start to unpack. But sometimes you will see there are many zeros which you can ignore, and so it's also helping you to calculate, okay? Can I go on? Very good. So we start with the bosons. But that's like the motivation and the story, so we start with the boson. So and the definition, I will just directly get the definition. So we are having our occupation space. So the definition is like that. Maybe I can use the color. So I'm defining the operator, which is called the creation operator, which if it takes some state, somewhere here is an E, at the end is an omega. And if there will be some any number, I don't know, here can be some any number even. Okay, A dagger E, and assume there is some number alpha, or alpha was between, I don't know. What's your favorite symbol for some number, if I just want to take a number? Alex, what would be yours? Huh? Alpha? Huh? What? 7. No, but let's put some complex. Or not like something like which is, you can put 7. Or I can use some, I don't know, Chinese symbol, but I don't know any of them. But okay, so I don't know. Some constant, Xi, okay? So this operator, now I'm giving the definition of the operator, is like that. Ignore the Xi, take it out. If it's a number, you can always take it out. And now looks here. You go to this position, and you take square root of this number which stays here. So it was 20, then it's 21. If it's 0, it's 1. And it's this state. Okay, this is the definition. Okay, and I'm defining the annihilation operator, AE. If it's a constant, NE and omega. I'm just taking constant out, square root of NE, and this is state N1, N2. And this is NE minus 1 and omega. Okay, so if you clearly see that if this is a 0, for example, if this is equal to 0, then basically what you get is that it's a 0 times something which is a 0 in such case. So it's a 0 vector. But it's a 0 vector, okay? It's like in each vector space we are having a 0 vector by definition. So we can understand it's going to the 0 vector, okay? Okay, so this is the definition, perfect. So in this picture which I was giving you before, if you are looking for this picture before, that we are having this big Fock space, and we chop this Fock space to the sectors. So this is the sectors, that's the name of that. Okay, so this is the different sectors. Then what we are seeing is that this A dagger operator is moving you in these directions. From sector with n particles, you go to the sector with n plus 1 particles. Because if the sum of all those guys was equal to, I don't know, x, some number, then the sum of all those guys is x plus 1. Okay, so it's moving you to the sector. And similarly, operator A is moving you in the opposite direction. Yeah? So A operator is moving you to this direction. Yeah? So you are going in the opposite direction. Okay, just to visually see it right there. Great. This is the definition of those operators. So I just define operators. And you see that I have many of them for each E, and E can be 1, 2, 3, up to omega. Okay, so I have so many operators defined now. Okay, great. So first thing which is nice about those operators by this definition is that they are Hermitian. So the first thing I will show, and we will clearly see that they are Hermitian operator. Hermitian in the Fock space. In the Fock space I define the scalar product, and with this respect to scalar product they are Hermitian. Okay, so let's do it. Guys, I'm apologizing that I'm writing so big, but yes.
So C is
Xi is a complex number, yes, scalar. And from that point of view, Xi is a complex number. because we allow the generic vector is the linear combination of such guys with this psi n1 and 2, so this is these things, yeah. Yeah. Yes? Yes. Yes, exactly, this is that. Yeah, so basically from this analogy with harmonic oscillator, it was generalized to this abstract picture. And a harmonic oscillator is a particular example, because in the harmonic oscillator you exactly do the things. Your alphas, alpha 1, alpha, omega, are eigenstate of the harmonic oscillation. So this is this energy eigenstates, and we call them normally n, right? But if you really write it as a wave functions, then this is this exponent times the Hermite polynomial, right? So in the X representation, it's some complex wave function. Yeah, but abstractly, we just call it n, eigenstate n, okay? Good, yes, that's that. Good. So, where's my coffee? He forgot? Can write him? Maybe he's already dating. Okay, so properties. So I'm writing the properties of that. And you will see that using this definition, many things in computation turns up very simple. Okay? So that's why I'm doing that. So let's see the things. Okay, so bosons. So definition you have, I don't need to keep it. So we write the properties. The first thing is, which I was saying, they are Hermitian with respect to scalar product. So the first thing, which I need to write is that A dagger E, AI are Hermitian conjugate. To each other. Okay, and it's very easy to see. So let's say if you take the scalar product of the state n1, ne plus 1, and omega, with the state n1 and e and omega. Basically, from definition, we know that this is nothing else as the square root of ne plus 1. Because the scalar product was defined like that, that those states are orthogonal to each other, right? So this guy is acting, it's producing square root of ne plus 1 and adding here. And there is n plus 1, so they are orthogonal, it's like that, right? You see it. Perfect. Now let's try Hermitian conjugate. So the Hermitian conjugate would be that we are writing opposite state. And we are writing the state AI acting on the state n1 and e plus 1 and omega. Okay? Great. So from the definition of that guy is going, he is seeing these things. He takes these things down, so it's putting this square root of ne plus 1 and then lower it. Okay, so I'm making it minus 1. So if I'm seeing, it's okay, square root of ne plus 1. Okay? Great, so they are Hermitian conjugate to each other. This holds for arbitrary n, so always argument is like that. You show it like that, and then you always say, it holds for arbitrary n1 and omega, so it's hold true for every state. We just check it on the basis, but if it's working on the basis, and those operators are linear operators, because I said on the constant, yes, come in. Yeah, shit. How much I'm owing you?
200块
Thank you. Where I should put the cap? Bring it to the Q-Fort?
哦，好，好，好，好。
Thank you. Well, next time I order a beer or some, maybe. Fried chicken. Or... Great, so this is the first property. The second property is that there is a very special state. There is a very special state which is called vacuum, but vacuum is not a zero state. So the second thing, there is a vacuum. It's called like that. The name vacuum is just name, okay? It's not what you think it can be another thing. It has a special name, so vacuum state is denoted like this. It's a state in the Fock space, which is zero's occupancy, formally. Here, very strong remark. If you take such state, and you will apply our equation star, you will get bullshit. It does not apply to this state. So this is some state which is added in the Fock space, we have it, but there is not a corresponding wave function which is given by there is a wave function, but it's not given by the prescription star, star, heart, okay? We can see it, okay? Just I want to tell it that, okay, to this state, this thing is not applying. One can write a wave function for it, but it's not given by the prescription given by equation heart, okay? Warning. And this state is defined by this property. The property of this state, so the definition of the state, it's a state which has this property that for all I from 1 to omega, if you apply the annihilation operator on it, you will get zero vector. This is not a zero vector because the scalar product of these guys, which itself is 1 by the definition. So it's not a zero vector. Zero vector is a vector whose scalar product with itself would be 0, okay? So just be aware of that, okay? Great. And if I am defining such vector, why I can define this vector? Because if I am seeing that if I start with arbitrary vector n1, n omega, and I will start to apply the annihilation operator, I will decrease all the time the number. So at some point I need to come to some vector from which I cannot decrease anything, which only can give me 0, okay? Great. And if I have such vector, then any other state can be generated from the vacuum, that any arbitrary state I can just write as acting on this state on the vacuum. Okay? Simply I start something and I'm adding numbers. Because in the definition of the creation and annihilation operator, I had this square root of n, I need to do this compensation divided by square root, such that I want to keep it normalized. Okay? So this guarantees that this state is normalized. Okay? Fine? Good. Fantastic. And now comes a very good thing that we will now start to play with these operators, because you see, yeah, but someone can say, but why you put operators in this way? Why you didn't put it in the opposite way? And things like that. So now comes the matter that commutation relation will make something for us. And since we are dealing with the bosons, we will get some commutation relations for bosons. And for fermions, we get a different one. So the information about the statistics will be then hidden in some order how we put the operators behind. Okay? Is that fine? May I go on? Great. So now we are going to do the commutation relations. And again, since I am too much writing, so I am clearing the blackboard. And we are going to the third property of that, creation and annihilation operators we have. Okay, third property is commutation relations. Maybe I can jump on that faster, or maybe not, so you will tell me. So third thing is the commutation relation. And what I want to basically do is that I want to prove the following things, that basically I can just write it that this is equal to 0, which is the same as this is equal to 0. And the thing that I want to prove is that I Ij is delta Ij identity operator, which we normally don't write, but I just explicitly write it, that there is the identity operator. Okie dokie. So, and the proof is done very simple. You take arbitrary vector from the basis and you show it on the basis vector. Since it works for every basis vector and the operators are linear, it works for all the Fock space. Okay? So, okay, let's try to evaluate firstly this on arbitrary vector. And then let's try to evaluate this on that vector. Okay. So we are going according to definition. This guy is going, he finds this thing, then he makes square root of nj plus 1 and put here plus 1, right? Then goes this guy. He comes here and writes the index. So this is the first result, and the second result is like that. This guy is going, finding this, doing what we said, square root of n plus 1 and rising, then goes this and do that. Okay? So this guy is doing this. Okay. And it holds for arbitrary. I can choose here anything. So we see that this is the same. So if I'm subtracting those two equations, so if I'm making a dagger E minus a dagger J minus a dagger J E, and I'm applying it or arbitrary vector, then I'm basically getting that this is a 0 because on the right hand side I have a 0. So first thing is proved. The second, you can do the second by the same thing, or you can do the following thing. Okay, oh, this is wholly for arbitrary vector. So what I can do, I can take this equation. So if it's working for arbitrary vector, then we also concluded it works as an operator identity. Yeah, this is the main point. So we show that this holds as an operator identity because it holds on any vector. So then I don't need to write vectors here, I can just write it directly like that. Okay? This is this logic, I think you saw it. Great. So this is holding, then I just take and I apply the Hermitian conjugation operator. And if I'm applying the Hermitian conjugator operator, I am getting this. Which basically is this, right? So, second thing is also proved. Great. So what I need to do, I just need to prove the last thing, and I need to prove that basically they are, in that case, that they are, in principle, they can, in some case, commute if I is different from J, but in general, they are not commuting, okay? So this is the last thing which we need to do. Okie dokie, let me drink the water. Let me do it. Great, so the logic is exactly the same. So let's say I want to firstly do it for E and J equivalent from this. So let me use what is on the blackboard. Okay. So let me delete it and let's try to prove it for that case. So let's do it like that. Okay. And assume that I is different from J for the moment. Okay. And again, we're doing the same game. So this guy is going. He's finding here square root of nj, right? And put it to nj minus 1. This guy is coming. He's finding square root of ne plus 1 and raising it to n plus 1, right? Pretty easy here. First guy is coming, so he's finding the square root of ne plus 1, right? Because this guy is mid here and raising it. Then comes this guy, nj, and lowering it. Again, I can subtract them. Let's say ij. Let's do it in that way, doesn't matter. Minus re plus ij. Acting on any vector of that is 0. Since it works for arbitrary vector, it's also true as an operator reader identity. So it's 0. I think we prove some part of that. Last thing which remains, we need to prove it for the case when E is equal to J. Okay, this is the last thing which we need to prove. So let's do it. So now I will again use the blackboard. Okay, you are still maybe writing. Great. So now I need to do last thing, and I need to prove it for the case E is equal to J, which is like the most difficult part for us now. So we are starting. Okay. So let's just do it. And we are going. So this guy is coming. And he is seeing here n, so he makes a square root of ne, right? And he would lower this guy by minus 1, right? Then comes this guy, and he see square root of n, he see ne minus 1, so then he write square root of ne minus 1 plus 1, and return it back. Okay, so at the end, what I'm getting here is that there is an E and here is nj. See it? Danny? Great. Let's do it in the opposite order. So this guy is coming. He see this thing. So we make ne plus 1 and rise it by 1. Now comes this guy. He see this. So we write square root of this and do minus 1, so at the end we are here. This is untouched. Okay. So what I get here is, if I'm taking those two numbers together, this is the ne. If I'm taking those two numbers together, I'm getting ne plus 1. Now let's subtract them. So I'm subtracting AE dagger minus AE dagger AE. Okay. I'm acting on arbitrary vector. And I'm saying that the difference of those two things is n plus 1 minus ne, or ne plus 1 minus ne, which is 1 times this vector. Right? Okay, great. So this holds for arbitrary vector, so it does not matter what is here, anything what will be here. So basically I'm getting operatorial identity that AE dagger minus AE dagger AE is equal to identity, which is 1. It's like the identity operator. It does not do with vector anything. Okay? So we prove it. Great. So why it's useful? Because, for example, now if I would like to work with bosons, so my bosons, as I wrote you, because of these commutation relations, I can write arbitrary of those guys. Just as I said before, that there is this A1 dagger to the power of N1, omega dagger to the power of N omega, square root of all those factorials. I can take the vacuum state. Okay. And since this is the bosonic operators, I call them A. And fermionic I will call C, such that we distinguish. They satisfy the commutation rule, so I can write it arbitrarily as I want, because there are always just the daggers here. And the daggers commute, so I can write it as I want. And if I will take now this guy, and I will make the equation hard, then you will see that the corresponding wave function is symmetric. If you make the anti-symmetrization, you will get the zero, and the symmetrization will be the same thing. Okay? So the point is that basically what we did is basically like if I am now taking the, let's say, okay, let's do it like that. So let's say I take my vector psi from the Fock space now. This is, let's say it is A dagger 3, A dagger 27 acting on the vacuum. Then it means that I have some state which looks like that. 0, 0, there is 1. On the position 27 is also 1, and all other guys are 0, for example, right? This is my abstract vector psi. Okay. Since I apply A operators which commute, I know it should be boson. So this tells me it is a boson. Okay. So this tells me that if I'm now applying equation number 3, or equation number hot, then it means that basically I'm getting a wave function psi, R1 and R2, which would be square root of 2 factorials divided by 1 factorial and 1 factorial. Right? This is this factor which was written in the definition. Because of the bosons, I should make this, right? And what I need to take the annihilation, I need to make the wave function of this, which is, let's say, alpha 3 at position R1 and alpha 27 at position R2, and I should make a symmetrization of that, which basically means that this is the 2 factorial divided by 1 factorial, and the symmetrization is 1 over 2 factorial, and I need to make the symmetrization. So it would be alpha 3 R1 alpha 27 R2 plus, because I'm making symmetrization, alpha 3 R2 alpha 27 R1. Okay, so this is the corresponding wave function in the X representation if you want. Okay, so this is the way how we will do it, if you need to do it. Okay, good. Other thing is that, okay, I have my state psi, and I would like to compute, or I want to verify whether it's normalized, because I said that all those guys are taking care such that if this was normalized, so if the scalar product of the vacuum with vacuum was 1, then it's guaranteed that all those states would also have a norm equal to 1. Let's try to prove it. Okay? So I will make a simple proof. Let me do it here. And then we go to fermions. Okay, so let's prove in this abstract way, so I'm working in the Fock space, that this is equal to 1. Okay. So what I need to do, psi is given here. Okay. If I am making opposite psi, I need to make this Hermitian conjugate. So it would be like this, and then I need to make the Hermitian conjugate, so it would be A27, A3. Okay, then it's going vector psi, which is A dagger 3, A dagger 27, acting on the vacuum. Okay, so now I'm doing calculation in the Fock space. Okay, so what I can use, okay, is it like that? Oh, I have it opposite, but does not matter. Okay, so what I can do is, okay, I can change the order of those two operators. but I need to use the commutation rule. So this is the same as A3 dagger, A3 plus 1. Here is the commutation relation. So this thing is now separating, okay? And then I'm getting that there is a R27, R dagger 3, R3, R dagger 27, okay? Plus identity, and then I'm getting R27, R dagger 27. Acting on 0. Good. So what I can do here, without any penalty, because 3 and 27 are different. Okay, they are the same modulo 3, but this does not matter, but they are different. So this I can write the same way that it is R27, R dagger 3, R dagger 27, R3, right? I just change it. And here I can also use the commutation rule. So it is R27 dagger R27 plus 1 acting on 0, okay? Is it clear what I'm doing? Just exchanging the letters, and sometimes I'm writing plus 1 using commutation rule. Okay, but this is the vacuum, and if the vacuum meets the annihilation operator, is automatically 0. So whatever is here does not count. Annihilation operator met vacuum, so this term will produce you the 0. The same here, R27, annihilation operator meets vacuum, so it's also 0. So what we get, that at the end, this is nothing else than the phi acting on the identity operator or on the vacuum, which is just the vacuum on the vacuum, which is 1. So we prove it. Okay? So proof in the Fock space are such that, so the calculations in the Fock space then turn to such things. That we are using the canonical commutation relations. And since we were talking with bosons in that case, we are using bosonic. If we would like fermions, we need to do the fermionic, and the calculation is a little bit different. But boson and fermions, we are treating on the same footage. Yeah, only sometimes we are using anti-commutation relations, which I will show in a moment. I think we are having a break now, right? Okay, doc. So after break, we will meet again, and we will do the fermions. Am I doing it too slow? Is it something boring? I can completely jump it. Just let me know, because I'm spending the time to explain the things, but I don't know whether you had it already during your university studies or in the previous lives. Maybe there is a Fock from the past as a new reincarnation. No? Okay. So how I am doing it? Slow or it's fine? It's fine. Okay, then it's fine. Great, we have a break.